everyone, this is part 2 in the video on rates of change. So previously we're looking at the average rate of change and the instantaneous rate of change. So remember, the average rate of change is just like your gradient function, sorry, not your gradient function, your gradient rule. Y2 minus y1 over x2 minus x1. So it tells us the gradient between 2 points, and that would give us our average. And instantaneous rate of change is the gradient at a point, so the rate of change at a point. So kind of if you can picture yourself driving from Kilbreda into the city. Now we know if we were to graph that, our speed, the speed of our car would change along the way. So while we're driving in Mentone, past the shops, we're probably doing around 40k an hour, but when we hit Nepean Highway, we're at 80 kilometers an hour, but when we're on side streets, we're probably doing 50 or 60 k's an hour. So the speed changes, but if we were to look at the average speed from Kilbreda to the city, you would look at how long it's taken you, all right, how far you've gone, the distance, and over time, all right? So that is your average rate of change. You can do your instantaneous rate of change. So if I wanted to, let's say I'm driving along Nepean Highway and I pass a speed camera, that is doing my instantaneous rate of change, my instant speed at a point. And it would be 80 because I'm a good driver and I do not speed, but that's pretty much the difference between instantaneous rate of change and average rate of change. The example we looked at, so I might just skip this one and go to the reservoir one, this one here. So we're looking at a reservoir being emptied. So I've got the graph of it. Let me just get it up. There it is. I'll get rid of the derivative now. So there's the reservoir being emptied. So we can see that at the very beginning, there's our maximum. For this graph, there are for this part of the graph, so we're only looking at really from 0 until it's being emptied at 90. So I might just limit my domain there so we can just see. So starts at, I think it was 729 million meters cubed, and then it's being, after 90 days, it's empty. Obviously you can't have negative volume, so it does stop there at 90. Now, the rate that it's falling, all right, it's not constant, it's not a straight line. Okay, so if we were to do a straight line going through that point and this point down here, that would be your average rate of change. Okay, so we've taken 90 days. So maybe I can do it on a calculator. Let's go to our main screen. I've done so many other things on here. So 90 divided by 7, 2, 9, 1, 2, 3, 4, 5, 6. And it's going to give me an exact value, so let's turn it into a decimal. All right, so it's really annoying. That should be negative. It doesn't really matter because it's going down. So that e to the negative 7 is not your exponential. That is times 10 to the negative 7. So we just need to move that decimal place. Actually, that's not. Or maybe that's the gradient. Yeah, if I put all those values in. So that would be the gradient of that line. So that would be the rate at what it is being emptied each day. But I don't like the fact that it's a negative 7. Oh, I think I did it around the wrong way. Silly me. I'm like, that doesn't look right. Oops. I want a negative. Sorry. Negative 729. Sorry. Did my values around the wrong way. Divided by 90. I was like, that doesn't look right. There we go. So it's decreasing at a rate of, what is that? 8. God, it's so hard, my eyesight. 3. So -8, basically 8.2 million per day. So that is your rate. So if I was to draw that as a straight line, which I can probably do, y equals, we need to start at the top, 1, 2, 3, 4, 5, 6, and it's decreasing at a rate of -8 point, I can't remember what it was, not point, sorry, 2, and then 5 ones. Oops, I got 2 negatives. And why did not work? Do I have too many ones? There we go. So there's your average. So that line represents, you know, the average that it's being decreased. All right, so if we're looking at a shorter amount of time, obviously that would change because you're looking at 2 different points, but the gradient of that line is the average rate of change, and I've just put the line there so you could see it visually. All right, so let's get back to this reservoir. So what we're going to look at today is, because we've already looked at the average rate and the instantaneous rate, we're going to look at the rate of the rate. All right, so our derivative function is the rate of change of our original function. So our second derivative is going to be the rate of change of our rate of change. So we're basically just talking about, all right, let's look at the maximum increase and maximum decrease in rate. So if you think about something being emptied or the speed, obviously if you were looking at speed, you could have, you know, you're faster at some points than you are at others. So that's what we're kind of looking at, the rate. All right, so if we're just looking at the derivative here, so obviously it's below the axis because we're going down. So your gradient is decreasing until it gets to 0. So this blue curve is our derivative, and that stops at 0 as well. So you can see that they both stop there at 90, 0. Your second derivative, and we might not do it in terms of this one because it's a little bit harder to see, especially because we're working with quite high numbers. So we might do that with a different question. Okay, so I just wanted to recap what that previous one was. And I've got so many tabs open. Anyway, let's move on. All right, so what we're going to look at is this example, but I might not look at it first. I'm just thinking whether it's best to look at this. Actually, I might look at this first because I'm going to explain to you how we can use the second derivative, and sometimes it's easier to explain it in terms of a context. So yeah, let's look at this example here. I might make it a bit bigger so we can see. Can we make it a bit bigger? Okay. So example 28 and example 29, it's the same context. We're looking at the number of bacteria present in a culture at time t. So we've got this rule, okay, here for n. At what time t will the population be a maximum? So we know up until this point, we find the derivative, let it equal 0, and that's going to give us our maximum. So that's basically what we've done here. So here's your derivative. And if you're doing this by hand, you could just use the product rule, and it's not a hard one to do without a calculator, but you can also do it on the calculator. This second one has just been simplified. You don't necessarily have to simplify it, and remember, unless it specifies to simplify, you just leave it, okay? Don't factorize, don't expand, just leave it how it is, unless it specifies otherwise. All right, so we're going to let our derivative equal 0. So our maximum population is at t equals 10. So we don't know what t is measured in, just time, so units of time. So if it was days, it'd be 10 days. If it was minute, 10 minutes, and so on. When you substitute 10 back into your original function, you get 132. So let's have a look at this graphically. So I think I've got one prepared already. So let me just just have a look. This one here, I think it is. We'll get rid of that tan actually. I'm going to pause. Alright, so I'm going to use different graphs later to explain the second derivative, but let's have a look at this one here. Actually, let's put those equations back up just so we can see. Alright, so the blue is our original function. Alright, so it's the number of bacteria at a certain time. We can see we've got a maximum here. So that's the maximum number of bacteria. So at t equals 10, we've got a maximum of approximately 132 bacteria. But we want to talk about what is happening at the rate of bacteria. So if you think about it in terms of our gradient, and it's so weird, I'm doing stuff with my hands, but you can't see my hands. The rate is increasing up until this 10, all right? And it's increasing at quite a fast rate. Okay, so between t equals 0 and t equals 10, that rate of change is quite high compared to, let's say, the next, well, it's never going to reach 0, but over the next 10 minutes, all right, it only drops by a little bit. Okay, so it's not as steep as it is in the first 10 minutes. So what your derivative tells you, so let's put the derivative up. And I'll zoom in a little bit so we can see. What our derivative tells us is what is happening with our gradient? What is happening with our rate? Is it increasing or is it decreasing? So we can see here, starting at 36, and it's increasing. Even though our derivative is going down, it's above the x-axis. So it's positive until it gets to t equals 10. Then it's crossing the x-axis, all right? So at that point, that's where we've got a stationary point. And then it's below our x-axis, and then it never crosses again because our original function, it reaches that maximum turning point, and then the graph then continues to approach infinity as x the graph approaches 0 as x is approaching infinity. All right, let's have a look at our second derivative. So our second derivative tells us the maximum rate of increase and the maximum rate of decrease. Okay, so it's a bit hard to get your head around. We're not looking at maximums and minimums. We're talking about decrease and increase. So with our graph, just get rid of that second derivative a sec. All right, your graph is increasing, all right, until it hits a certain point, and then the rate is decreasing. So if we want to look at the maximum rate of increase and the maximum rate of decrease, we're basically looking at the maximum and minimum of our derivative function. So let's write that down. Let me just go to all my notes. I might write that on the last page. I was going to do an example here. We might still do that. I'm going to leave that there for a sec. Ugh. All right. The annoying thing with this computer is when I want to write, I have to flip it over. Okay, so the maximum rate of increase and the maximum rate of decrease. Okay, so this is where it's important to look at our graph. So we're referring both times to a maximum. All right, so it's either like if you think about turning on the tap of your bath, all right, the maximum rate, if you know, as soon as you turn it on and the water rushes out, and then you're like, oh gosh, it's splashing everywhere, and then you turn it off, not turn it off, but you turn it down a little bit. So that first whoosh of water would be quite a high rate of increase. All right, so it's increasing at quite a high rate. And let's say, you know, you're in the bath and you filled it up too high and you've water, you got to let a little bit of water out of the plug hole. So you're just, you know, lifting that plug just slightly up so a little bit of water is being let out. Okay, so, you know, that would be your maximum rate of, well, if you're emptying water, because, you know, you can have it could be 0 if it's not being emptied. But if we're just lifting it and letting that water out and it's slowly going out, and then you know, take it fully off, your maximum rate of decrease as it's pouring out would be when that plug is fully out of the plug hole. So you could let it out a little bit of water. Okay, so you think the volume of water is decreasing. As you take that plug all the way off, it's going to be increasing at the amount of water going out of your bath is at its maximum. All right, the rate that it's going out. And then you might put the plug back on and just let it out slowly again. All right, but it's, you know, the rate that it's going out of the water, sorry, not out of the water, out of the bath is the maximum rate of decrease. All right, that's probably not the best example, but we're looking at maximum rate of increase and maximum rate of decrease. So let's go back to our graph. So let's look at this black graph, because this black graph is our derivative and it tells us where our maximum rate of increase is and our minimum rate of decrease. So our maximum rate of increase is the maximum point of our derivative. All right, so here, they're at 36. So the maximum rate is 36 bacteria per unit of time. So if it was days, 36 bacteria per day, or if it was seconds, 36 bacteria per second. All right, that's the maximum rate. The minimum rate is of the maximum rate of decrease is your minimum point. All right, because we're below. All right, so it's going out. Oh, it's going down. Sorry, I should say. So it's going down, but the maximum point is your lowest point. The maximum rate of decrease is the lowest point. So it's at t equals 20. And it's a negative value, so negative 4.872. That negative just tells us it's decreasing. So the maximum rate of decrease is 4.872. Okay, so notice how I didn't say the negative. So we're saying the negative is the decrease part. So it's decreasing at a maximum rate of 4.872 bacteria per time unit. All right, so if we look at our second derivative, actually, let's not look at the second derivative. Let's look at hold on. I'm going to finish this off. So the maximum of your derivative and the minimum of your derivative. So when f dash x is less than 0 and when f dash x is greater than 0. Because when it's greater than 0, we have an increase. When it's less than 0, we have a decrease. All right, let's go back to this example. Sorry, just scrolling. Okay, so in this example 30, we're kind of leading on. So we've still got the same function. Sketch it, so we've already sketched that, so I'm not going to sketch it again. We can see here on the solution it's been sketched. We want to find the maximum rates of increase and decrease of the population. So we can see here we've got our original function and here's our derivative function. The maximum of our derivative function is here, all right, at 36. Our minimum we can see is roughly around here. It's a bit harder to see, but we can actually see that it's a turning point. So to get that value, All right, and what we've got here, what they've done is they've let RT equal the derivative of n. All right, so what I'm going to write on the side here is that RT is equal to the derivative of n with respect to t. The derivative of r with respect to t is the second derivative of n. All right, usually we would use a second derivative, but I guess they're just using this notation to show you that it's the derivative of the rate, which is the rate of the rate. Okay, so we've got the maximum rate of increase, all right, is at 36, at that highest point. Now your maximum rate of decrease, we can see is roughly around 20, but it's a bit hard to see, but we can see that it's a turning point. So it's just like when you were finding a turning point for a function. So if we were to find the turning point here, we would take the derivative and let it equal 0. We can do the same thing here. We can take the derivative of the derivative and let it equal 0. So that's what we've got here. Here's the derivative of the derivative, and we're going to let it equal 0. And that happens at t equals 20. All right, so that turning point is at t equals 20. So your minimum value of r occurs at t equals 20. But how we interpret that is the maximum rate of decrease. And it's negative here, but remember that negative is your decrease. So we say it's 4.9 bacteria per unit of time. All right, so don't say negative 4.9. It's like if you lost weight, you don't say, I lost negative 5 kilos. If you lost money, you don't say, I lost negative $10. All right, you just say, I lost $10. I lost 5 kilos. All right, so just be careful with that. So if it's a rate of decrease, all right, we don't have a negative. It's always positive when you're interpreting it. Okay, so with our second derivative, let me just think. In terms of these questions, and I'm going to explain it a little bit later in terms of stationary points, how we can use the second derivative for stationary points and points of inflection. Okay, so basically what we're looking at now is just maximum rate of increase and maximum rate of decrease. All right, so we've got another example. So the number of insects in a population at time t is given by. So this example is very similar to the one before. So if you want to have a go at doing it on your own, please do. We're going to sketch first of all nt and then the derivative, and we're going to find the maximum rates of increase and the maximum rate of decrease. All right, so let's have a look at what it looks like graphically. I don't think I've done this one yet, but it's very similar. So all we need to do is change some numbers. What was it, 50t? Pretty much the same, except for changing that 36 to be a 50. All right. And can't really see the graph too well, so let's just do that. Okay, so there's the insect population, I think it was. We can see we've got a maximum up here at t equals 10 again. So the maximum population is 183.94. So basically 184. The minimum population, you can see it's getting very close to 0. But if we're looking at the rate, right, in your first 10 units of time, let's call them days. The first 10 days, we have quite a steep increase. And then we've got quite a steady decrease as it approaches 0. So with your derivative function, it's showing that rate. All right, so it's above the x-axis between x equals 0. Can I just, there we go, x equals 0 and x equals 10. All right, because we've got a turning point at 10. So it's above the x-axis, so it's a positive gradient. But at 10, it is, there is a turning point, and then it's decreasing. All right, so you can see our graph is going down. and it's slowly approaching 0. So to answer question B, the maximum rate of increase we can see just the maximum point of our derivative function. Now that maximum point is not a turning point. All right, it's just 50. Okay, so it's 50 in secs. Oh no, sorry, not 50 in secs. T equals 50. No, it wasn't. It was 50 in secs, sorry. What am I doing? 50 in secs per unit of time. All right, and the maximum rate of decrease, sorry about the spelling, there we go. All right, is where this minimum turning point is, which is here. All right, we can see that at t equals 20. Now, if we were to do that on our calculator, all right, and I've probably already done it somewhere, but let's just do it again. Let me just think. Okay, so if we're finding the derivative of that, I'm just thinking if we could do it all in one go, but, oh, sorry, one button. Okay, let's find the derivative. There we go. 50. I'm just using x, but just make sure you transfer it properly. Times e to the power of negative 0.1x. Did I put that in correctly? Okay, it's in decimal. I prefer exact, so I'm just going to change it back. Very temperamental. Come on. All right, it's just easier to read it if we've got that. Okay, so we know from our knowledge of using the calculator, I'm going to highlight that, copy. Let's go down to this next line. And we can just go to calculation and function min. And we can just paste it in. All right, so we can see the minimum, that's your turning point, but remember that negative is your decrease. So we're looking at the rate of decrease. We don't need that negative there. So it's 50e negative 2 insects per unit of time. And you could also get that by substituting t equals 20 back into your function. All right, so that's the maximum rate of increase and maximum rate of decrease. Your second derivative, if you wanted to do that, let's just go here, so it's a bit easier to see. All right, it's a bit hard to see, but it actually crosses the axis at t equals 20. All right, so that's the same as where our turning point is. Okay, so the same theory when you did the derivative. So that also helps us to find out where there's an inflection point. Okay, so an inflection point is when your graph goes from concave up to concave down. So we'll talk about that in a bit more detail in a sec. All right, let's just do the next question. I can scroll down. All right, water is being poured into a flask. The volume of water in the flask at time t seconds is given by. Find the volume of water in the flask when t equals 0 and t equals 20. All right, let's try to do, I haven't done this question yet. Most of these I've done because I did a video before this one and I wasn't that happy because my dog was barking and yeah, I just wasn't that happy. So here we are. All right, so I'm going to define this. Just define it once. Now, I would strongly encourage you, if you were doing this in an exam, to probably use the variables that we've got there, v and t. I, however, prefer f. Whoops, let's start again. I missed a space there. I'm going to do f of x, but you really got to be careful. If you think you're going to get confused, you need to put v and t on. All right, equals. Oh, God. Sorry, guys. 3. Hopefully you're writing it in at the same time on your calculator. Open circle, open bracket, 10x squared minus t, so x cubed over 3. Maybe type a 3 in. Come on. Okay, I'm going to flip this over. Maybe it'll cooperate if I use my keyboard. There we go. All right, and we've got a restricted domain. I'm going to put that in here in my define. So to restrict the domain, we can just say given that, and we're going from 0 to 20. All right, so it's good to restrict it because further along the line, we've got a cubic here, so it might, your maximum is going to be infinity and your minimum is going to be infinity. So if you didn't restrict it, it's going to be hard to do. All right, so find the volume of water in the flask when t equals 0. Okay, so because we've already defined f of x, that's basically saying, hey calculator, how you doing? Can you remember this function? So I just need to type in f of 0. There it is, 0. Okay, you can do that by hand quite easily. Then the second part, let's do f of 20. There it is, 1,000. So if I was to graph this, I know it starts at, I've got 0, 0, and the point 20, 1,000. Find the derivative of v with respect to t, the rate of flow. So if you wanted to do this, you can just go to, there's several ways. I did it differently before. You can do f of x this way, and we don't need to do it at a point. So there's your derivative, or you can do it from your keyboard. So we're just doing derivative with respect to x, f of x. You can do it that way as well, or you can also go to action, calculation, and don't know whether, yeah, there we go. Okay, so many ways you can do it. All right, so there's your derivative. Sketch the graph vt against t. Okay, so if we're doing this, that was just my Lucy just barking at the neighbor. Okay, what we were doing, graphing. Okay, so let's graph. So I'm just going to clear what I've got there. I don't like it. Okay. I thought I cleared you. I cleared my graph. Okay, so if I'm graphing the derivative, no, sorry, the function, sorry, the wrong one. You can just type f of x. If I go straight away to graph it, you might not see it all. See, it says from 0 to 20, and I already know that my two endpoints are 0, 0, and 20, 1,000. So with up the top here, you can change it. This one here might make it a bit nicer, but yeah, I don't know. I just like this one. We can just change it what we like. I don't like starting at 0 though, because sometimes it's a bit hard to see. So let's just go a little bit further. So just so we can see it a bit easier. The y minimum will do the same. And what we're going to, 1,000. Let's go a little bit above 1,000. Whoops, not that much. All right, so there's our graph, and we know it's a cubic, so that's why it probably goes like that a little bit. Okay, so there's our answer for C. So if you were sketching that, you need to put your two endpoints on. So your endpoint here being 21,000 and your endpoint here being 0, 0. I can see we've got a point of inflection along the way. So we'll talk a bit more about points of inflection in a sec. All right, so sketching the graph of the derivative. Okay, so here, if I just go to keyboard, and I can do that here. All right, and just tick it, and there it is. So we can see, let me just drag it up. Why did that keep going past when I restricted it at 20? Don't know. So my derivative should have finished at 20. Let's just restrict it now. I probably should have, I'll do it properly with my keyboard. Whoops. Okay. I thought because I restricted it with my original function, it should have restricted that as well. But anyway. All right, so there's our derivative. If you wanted to sketch them separately, which might be a good idea because then it's a bit easier to see where your, the maximum rate of increase for your derivative might be a bit easier to see if you had a better scale. All right, so what time is the flow the greatest and what is the flow at this time? So what we can do is have a look at that turning point for our red function. So let's just do it this way and then I'll show you using this second derivative. What am I doing? Okay, maximum. So we can see it's a maximum. Now see how your graph is flashing. It's not a disco. It's just saying, would you like to use this function? No. I want to use the other one, so I just use the cursor to go down and then we're having a disco with the other one and then just press enter. Or not. Let's try again. All right. Function max. All right. And then we want to go to the not found. What do you mean? Should have found it. All right, let's do it on our, don't know why it's not working. Let's go back to our main screen. All right, so there's our derivative. Actually, I'm going to highlight that, copy. It's probably better to do it on this screen anyway because on your graphing screen, it'll always give you an approximate answer. It won't give you an exact answer. So function max. Now I'm nervous it's not going to work. There we go. I don't know why it didn't work before. So the maximum value is 75 at x equals 10. All right, so in the context of this problem, it is... I'm just thinking, sorry. It is t equals 10 and your maximum rate of increase is 75. All right, so let's write that down. Can I write it like this? Maximum rate of increase, save me flipping my computer over. Maximum rate of increase is at t equals, what was it, 10? No, was it 10? I can't remember now. 10, and it was 75. So it's 75. What is our mils per second? All right, so that's our maximum rate of increase, our maximum flow. So, and what is the flow? Sorry, yeah, so that's what I've done. T equals 10, so 10 seconds, which I probably should write, 10 seconds at 75 milliliters per second. All right, so let's go back to our calculator and I'm going to highlight our derivative function and copy that. I think I already had it copied, but we're going to copy it again. Go back to our graphing screen. Oh, sorry. Aren't you working for me? Okay, we're going to put the derivative of our derivative in. Actually, let me show you. You don't need to show you another way. You can do second derivatives this way. So d2, so your second derivative, and then you can put f of x. Alright, so if we sketched all three, see how it's quite hard to see the green graph? So we can change our y-axis. What am I doing? Changing our y-axis. Oh gosh, okay, sorry, just had a bit of a blank. What do you reckon, 20? I'll do negative 20, maybe a bit easier to see. There we go. All right, so can you see where it's crossing your x-axis? So that is where your turning point of your derivative is. Okay, so that should be 10. So if I go back to here and we want to calculate, actually we can just go, I'll just do this. The x value when y is equal to 10. We've got to choose our graph though, so we're going to have a disco with that one. Alright, we want the x-intercept, so y equals 0, so you can see there it is at 10. So going back to your main screen, I did the max here, but if you were doing it by hand, you could just find the second derivative, like we did before. Where are we? This button here, second derivative of f of x. So you're taking the derivative of the derivative, which is not hard to do if you've got like an easy derivative. Okay, so there it is. So if we let that equal 0, which I'm going to have to go solve equals 0, comma x, we should get 10. Okay, so there's many ways you can do it. You don't have to use the second derivative, but some people do like to use the second derivative. Okay, let's have a look at what else the second derivative tells us. Okay, so I'm going to show you what is in your textbook, if I can find which tab it is. All right, so your second derivative, we've just looked at it in terms of maximum rate of increase and maximum rate of decrease. So that's in your textbook too. There. Okay, so basically, I feel like I've kind of explained it a little bit better than that little short bit there. But we can also use the second derivative to help us sketch a graph. So what we mean by concave up or concave down is whether your graph is up or whether it's down. So if you kind of think of a bowl or maybe even a parabola, if it was a positive parabola or your bowl is upright, so maybe you're eating your Weet-Bix, that's concave up. Your bowl is up. All right, if you've like, oh, I don't like Weet-Bix, and you just crack a tanty, put it upside down, it's concave down. I don't want to eat those Weet-Bix. You put your bowl upside down. Okay, so think of it in terms of a bowl. If your bowl is upright, concave up. If your bowl is down, it's concave down. So what your second derivative can tell you is a point of inflection. Okay, so two things I'm going to show you now with the second derivative is point of inflection and also how we can use the second derivative to tell us what type of stationary point it is. So we've got here in the book just two examples, and Siri's going off at me. We've got a quartic, first of all. So in this quartic, we've got some stationary points and we've also got points of inflection. So I've got a point of inflection here at C and a point of inflection here at D. So from negative infinity to C, the bowl is upright. All right, it's concave up. From C to D, your bowl is down. So maybe you thought, oh, here's my cornflakes. And you're like, yum, yum, yum. Oh, no, it's not cornflakes. It's Weet-Bix. And then you put your bowl upside down. And then you're like, oh, I didn't realize I don't mind Weet-Bix. Or you're hungry, so you put your bowl back up. All right, so concave up, concave down, concave up again. So we're going to use this example here of this cubic, only because it's a function there and I really couldn't be bothered trying to think of a quartic to explain it to you. So we've got some stationary points here. All right, so I'm going to show you how we will find what type of stationary points they are using the second derivative, and also how we can find this point of inflection. So it's quite easy to see on this graph what the where the point of inflection is. So the point of inflection is just where it goes from concave up to concave down, or vice versa. All right, so let's go back to one of these documents. Okay, sorry, a little bit wonky. And I think I've done this one on Desmos, so let's see if it's one I've prepared earlier, this cubic. Okay, so here's a cubic, the same one that was in your textbook. So if I just go, there's our, we know there's a maximum turning point there and a minimum turning point here. All right, so let's just assume we did not know that. So kind of ignore that stuff there and we'll just move on. So we've got f of x equals 3x cubed minus 4x plus 1. I'm pretty sure that was it. Beautiful. All right, so there's our function. Now, if we were sketching this, we would find our x-intercepts, and we can see our y-intercept is 1. Okay, so we know how to do that. Let's now find where there are stationary points. So we know there's stationary points when the derivative is equal to 0. Oops, can't spell stationary points. All right, so your derivative is 9x squared minus 4. All right, so we're just finding the derivative of f of x. Easy. We let that equal 0 because we know at stationary points our gradient is 0, so we'll quickly solve that. Being quick and I make boo-boos. 4, and this is 4 over 9. And I'll just do it over here. So x equals plus or minus the square root of 4 over 9. So we're going to have square root of 4 over 9. Square root of 4 is 2. Square root of 9 is 3. So we're going to have negative 2 on 3 and positive 2 on 3. Now we know we have stationary points there. Up until this point, and you may have been shown how to use the second derivative to decide the type of stationary point, but up until this point we would do a table. All right, we'll have our x values. So we know at negative 2/3 our gradient is 0. So that's not a negative sign, it's a flat gradient. At 2/3 it's 0, like flat ground. And we would say, well, what's happening between those points? So we choose a value that's between negative 2 on 3 and 2 on 3. Now we don't want to be fancy and say, oh, 1, I don't know, 1/4. All right, just do 0. Do easy ones. Okay, there we go. Negative 1, 0, and 1. Easy to substitute into f dash x. All right, so first of all, substituting in negative 1. So here's our derivative up here. So 9 times negative 1 squared, so 9 minus 4. It's going to give us 5. Doesn't matter what the value is, it just matters whether it's positive or negative. So if you're finding it hard to calculate, as long as you know whether it's positive or negative, so it's positive. All right, then at 0, I probably should put a 1 there. Sorry, let's just change that. Or negative 1, I should say. At 0, we're going to have negative 4, so it's a negative gradient. And then the derivative when x equals 1, we're going to have 5 again. We're going to have a positive. So we know that, so the graph of our gradient is going to go like that, which we know from graphing it before. So that's how we would do it in before now. And you can still do it like that. I really like that way. It's quite visual. If you're using the second derivative, and I'm going to do it in yellow. Whoops. So the second derivative, we use 2 dashes. All right, so that's going to be 18x. We know there's a stationary point here at negative 2 on 3 and 2 on 3. So we substitute those two values in. So let's do negative 2/3 first. Just because it's a fraction, don't let it scare you. You only need to know whether it's positive or negative. And clearly, because we've got a positive times a negative, it's going to be a negative. And the answer is negative 12. All right, but you just need to know whether it's positive or negative. So if you're sitting there thinking, oh, my brain doesn't work, then yeah, you just need to know whether it's positive or a negative. And then for the next one, we're going to do 18 times 2/3. So that's positive. Now, this being negative, oh, that's terrible, sorry. Oh, that's going to get rid of everything. It's highlighted in a different color. This is going to be any better. All right, so this is negative, and this is positive. When your second derivative at a point, your stationary point, so let's call that P, whoops, is less than 0, we have concave down. So it's like that. Bowl's upside down, Weet-Bix falls out. No more Weet-Bix. When your second derivative at a point is greater than 0, we have concave up. Oh, I've decided I like Weet-Bix. Now, we know that from this diagram here. Whoops. That was meant to be highlighted. All right, from this diagram here, which I just scrubbed out. And also from our original graph. Okay, so instead of doing that table, you can just do the second derivative to test whether it's concave up or concave down. Now, the other thing that your second derivative will tell you is where you have an inflection point. So when your second derivative is equal to 0, and I might do that here, so when your second derivative is equal to 0, we have what's called a point of inflection. So let's just do that. So 18x, no, sorry, what am I doing? Sorry, I was doing it right. 18x equals 0. In my head, I had the answer is 1, but x equals 0. So you have an inflection point at x equals 0. So if we were to substitute 0 back into our original function, all right, back into here, where are we? All right, to our original function, f of 0, basically we get 1. So we have an inflection point at 0, 1. So let's have a look at our graph again. Dun, dun, which one is it? We have a point of inflection there. It's also our y-intercept, just happens to be for this one, but you can kind of see it a bit better in the textbook. All right, so we can clearly see it's concave down until we get to 0, 1, and then it's concave up. All right, so that's what your second derivative can tell you about both your rate of, your maximum rate of increase and maximum rate of decrease, your stationary points, and your points of inflection. All right, girls, bye-bye.